Hi, my name is Florin. I'm a cryptographic engineer at TACEO, and I will be talking a bit about lookup tables in CoSNARKs. So at the beginning, I want to give a quick intro into secure multiparty computation, so for short MPC. So in MPC, multiple parties can compute functions over their secret inputs while keeping these inputs private. So there are many different protocols and security levels to it. So semi-honest versus malicious security, honest versus dishonest majority, and there are many protocols. MPC is capable of supporting privacy across a range of applications, so such as privacy-preserving data analysis, threshold signatures, digital wallets, and importantly, in the context of this talk, collaborative SNARKs. So how does MPC work? So at the core of MPC stands the concept of secret sharing data. And with secret sharing schemes, you have your private input and you want to distribute it to possibly untrusting parties to compute on it. Therefore, it is important that the shares do not leak anything about the underlying data. And how to achieve this? For example, in additive secret sharing for n parties, you pick n-1 random shares, and then you get the last share just by the difference from the previous ones. And the nice thing about secret sharing schemes is that it is linear, so meaning that you can do linear combinations on the shares and the underlying data gets modified accordingly. Where you have to do interaction between the parties is when you multiply shared data. And this is why in general you have to be careful with non-linear computations such as multiplications, since communication is often the bottleneck in MPC protocols. And of course, why we are doing MPC is that the inputs remain private and also the intermediate results remain private and unknown to the parties. And also if you XOR these pictures there, you get the original cats. So what are collaborative SNARKs then? These are computing basically a SNARK in MPC, where the private secret witness is secret shared among the MPC parties. And these then do the proof computation on these shares in MPC. And then you get a proof out of it, which is not different to one from a single prover. And the big question then is, why would you want to combine these two things with overhead? So we have two primary use cases. The first one is private proof delegation, where you want to outsource the proof generation from, a handheld device, which is not so powerful and can't do the computation in reasonable time. But the problem there, if you just upload your witness to someone, you leak the witness to the person and you have to trust them. So this is where MPC comes into play. So you secret share your witness and then an MPC network does the computation for you. And recently we launched the TACEO proof for beta testing. So this is our solution for private proof delegation. At the moment it works with Circum and the CROF16 prover, and also in the future our CoNoir implementation will be possible to do with TACEO proof. So check out the blog post on the right if you're interested. And the other use case we see is private shared state. So blockchains, like for example Adstack, they store their commitments on chain. But the question then is, how can you compute on these when you have a sensitive input from multiple parties? And to do this with CoSNARKs, you have to do all this stuff, the SNARKs and so on in MPC. So what about the performance of CoSNARKs? Are ZK proof systems MPC friendly? So for SNARKs, we are mainly dealing with linear operations, which we said before are nice in MPC. So FFTs, MSMs, evaluating polynomials at public points, sum check, and so on. Examples of such protocols, CROF16, Blanc, Ultrahong, Halo2, and so on. Other KCG IPA-based protocols. On the other hand, most STARKs, they construct a Merkle tree and require many hash valuations, which is not so nice in MPC because it's not so linear, yeah. But there are tricks to deal with that also in the STARK case, but that's another story. Okay. I think it's lagging quite a bit, sorry. Okay, now it stays, I hope. So one challenge in CoSNARKs is the extended witness generation. So there are quite some few papers on collaborative SNARKs, but what is often missed out is the extended witness generation. So these papers, they focus on the components of the proof system and only briefly mention this witness extension. So we want to kind of distinguish this into two parts. So the first one is where you have your program, your circuit, and you basically compute the circuit on the input and then get the witness out of it and maybe some additional outputs. So this basically requires an MPC VM. We have stuff we have to do there like bit decomposition, lookups, ROM-RAM operations, etc. The good thing is if you're just doing private proof delegation, you don't have to care about these things. And then the other part, which belongs to this extended witness generation, is the trace building. So where you have to do additional computations and witnesses on those witnesses and put this into the trace. Okay, so now let's talk about lookup arguments in ZK proving systems and what challenges they bring to the MPC setting. Okay, so why are lookup arguments necessary? So they are used to prove operation statements which are expensive in ZK. For example, range checks, bit operations, elliptic curve operations, S boxes, and so on. So instead of doing these computations in ZK, adding many constraints for it and so on, you use lookup arguments, and then you prove that these input-output pairs belong to a certain table. So there are different techniques for it, such as plookup, lookup, and others. So we've heard it before in the intro. So what does this mean for our case, for the MPC case? So we have to do the lookups during the witness extension because we need the results for these lookups to actually continue the computation and get the witness out of it. And then we also have to deal with the lookup arguments during the trace building, which we'll have a look at a bit later. On the other hand, the lookup stuff related to during the actual proving, so where you actually prove the stuff, that is no blocker, this is just minimal overhead in MPC. Yeah, now we... Okay, so we just said range checks are a possible application for lookups, and there is an alternative for it. So this is how it is done in Barettenberg, so Aztec's proving backend. So say we want to range constrain some values, x0 and so on, that these are in the range smaller to 16. Then we create a list with these elements, put the upper and lower bound in it, and also add our multiples of 3. And then we sort this list, and then we know that the neighbors in this list, they have difference at most 3. And we also have the lower and upper bound there, and yeah, then we should know if the values are in this range. So what this requires in MPC is oblivious sorting, and we need it to be oblivious because otherwise we would leak something about the underlying values. The main operations for oblivious sorting are you need to do comparisons in MPC, and then you have to swap them, so doing a CMAX depending on the output of the comparison. So in our implementation in CoSNARK, we use this oblivious radic sort from 219. Another option is the batcher out even merge sort, which is a bit slower, but yeah, also works. Yeah. Okay. Now let's have a look at more general lookup tables. So you have an input, and you want to look up the output value in the table. Again, we have these examples: bitwise operations, S boxes, so on. So we have some input X, and we want to get the output f of X. The question again is how to do this in MPC. So you could hope that there are more MPC-friendly cases, so where you really can efficiently compute this function f in MPC. But in reality, unfortunately, often CK and unfriendly also implies MPC unfriendly. There are still some cases which are more convenient. For example, for bitwise logical operations on field elements, you convert them to binary shares, do your binary bitwise operations on these shares, and then you still have to convert these back. But for other cases, you will need a general purpose MPC lookup protocol, which also have a look at later. Additionally, what is not helping this function approach where you compute this function in MPC is that you often have to decompose your field elements into smaller chunks, and then you do the lookups on these slices. So this means even if you have some dedicated protocols to compute this function f, this is probably only helpful in the witness generation phase, because in the trace building you will usually need these slices as well for the trace. Therefore you not only need MPC protocols for the lookup itself, but also for this decomposition of the values before the lookup. Okay, now let's have a look at what this lookup protocol introduces to a problem. So in lookup, you have to remember or count how many times a certain value has been looked up. So like in this table, for example, entry 1 has been looked up 7 times, and you have to do this in MPC. And this counter then is later used in the constraints of the proving part. And yeah, compared to the non-MPC or plain CK case, this is substantially more difficult, since in plain CK you can just increment your counter, but in MPC you not only have to do this lookup in a secure way, but also do the counter increase without leaking anything. Now we have a another related topic in SNARK systems, that is ROM and DRAM operations. So we see some noir code here on the side where you have some input array, and you want to write and read to this array in an oblivious way. So we have to find some MPC protocol to do this, because we have potentially secret shared arrays and indices where we have to read from and write to. And this is something that already happens during the witness extension phase, and then later again in some form during the trace building. Now we come to the part what MPC lookups are and how they can be done, and also about this writing RAM operations. So these are the two main operations we need or we are concerned about. So the first one is lookups on shared indices. So we have some array and indices given, which are secret shared values possibly. And we want to, for I, look up the ith value in this array and get the secret share of the xi out of it. And the other cases where we want to write to this array. So we have some secret index I and some secret value yi, and we want to write this to the ith entry of the array. Okay, let's look at how we implemented this in CoSNARK. We based it on Maestro, which is a MPC protocol for evaluating in an MPC way the AES encryptions. So it is focusing on the S boxes part of AES. So the main point of this protocol is how you can efficiently turn your secret shared index into a one-hot encoded vector so that you get a vector of secret shares where only the ith value is a 1, other ones are 0. And we used this protocol and implemented it for reads and also extended it to lookup writes. So the high-level approach, how you do it for lookup tables of size 2 to the k is you recreate this one-hot vector. For example, if you have k equals 2, you have the secret share of the index 2, and then you get this vector out where so the 2th entry of the array is 1, other ones are 0. And this requires to communicate to the k-1 bits in k-1 rounds. And we will see now how we can use this for reading. So we have this one-hot vector from our secret index I, and then we get our secret share by doing this dot product between this one-hot vector and our array. So in the honest majority MPC case, this dot product can be done quite efficiently with communication of one field element, and in the case the lookup table is public, we don't have to do any communication because it's just additions and multiplication with public values. Okay, and how can we use this for writing to tables? So say we want to write an element x to this to our lookup table. We can create this one-hot vector and then basically CMAX the whole table with the one-hot vector. So you can see that we write to the ith entry exactly when j equals I, and we can do all these CMAXs in parallel. So we only have one communication round for this. And yeah, how can we use this for this lookup program we talked about? So how do we count the values for the looked up values? We create a one-hot vector for the secret shared indices, which we know when we are layouting this table, and then we just have to sum up these one-hot vectors and get our counts from it. Okay, so now that we have all these pieces we needed, how can we use them in our CoSNARK implementation? So I've said it here and there. We implemented all this stuff in our CoSNARK repo. So Noir is Aztec's ZK language, and we also implemented the ultrahonk prover. Yeah, we have this oblivious radic sort, which we are using for the range checks, the Maestro protocol for ROM and RAM reads and writes, and all these black box functions that exist in Noir, like MSMs, char hashes, bitwise operations. They use these techniques for lookup. So we have to count the lookups, fill the input-output lookups into the trace, and so on. So how this looks in practice, for example, if we have a bitwise AND, we have to decompose these field elements. We do this via garbled circuits. Then we can do there the bitwise operations, and then we have to convert it back to the arithmetic shares. Okay, so what are possible improvements there for the future? So we could investigate more dedicated or specialized ORAM protocols where we don't need to hide the access type though, because typically it is known as the circuit is usually public knowledge. One thing you also have to think about, combining ORAM with generic MPC protocols is not always trivial, and we have to do extra considerations there. And what we also really like to have is some way of keeping results from this VM part where you compute the witness to the trace building part, because we do a lot of duplicate work and we have all these intermediate results already in the witness generation, and then we have to do it again in some way in the trace building. So it would be nice if we could kind of keep this there. Let's have a quick look at some numbers. So here we have a comparison of this Maestro approach we implemented versus a more trivial approach where you just go through each index from 1 to the 2k with the secret index and do a comparison, which gives you a share of 0, 1, and then you put all this stuff into a vector. I think we can all see how much more efficient this Maestro approach is to the trivial approach. One thing that's left out here is that you have to do this conversion from arithmetic to binary shares beforehand because the Maestro protocol demands it. So that is left out here. Okay, to sum it all up, I think we all know that lookup arguments are beneficial to improve the prover performance, but on the other hand, they introduce some challenges when you're trying to do this in MPC. This calls for more research on CoSNARKs. So on the one hand, for Graph 16, which doesn't have these fancy features, we are at essentially no overhead. But when you introduce all these lookup tables, decompositions, and stuff that actually make things more CK friendly, they make stuff less MPC friendly. Maybe it is even necessary to take a step back, so reduce CK friendliness in some way to gain more MPC performance. Or why not both? That would be even better, of course. So for the CK lookups, they require us to do this oblivious sorting, these table reads and writes in a secure way. We have our implementation on Maestro, and this is all implemented in our CoNoir library, where we are at the moment focusing on feature completeness, so implementing all these black box functions and stuff like that. And then have a lot of performance improvements and optimizations planned for the future. Here are some links. There's a link to Franco's workshop at the last ZK Summit, to our docs, our blog, and our repository where all the implementations live. Maybe I'll just leave that here. And thanks for your attention.
Hi. I had a quick couple of questions. Is your MPC semi-honest or malicious?
It's semi-honest, yes.
And these benchmarks, how many parties, what network latency, are they in the same zone in some cloud or like across?
They were some AWS servers, so they were co-located, I guess. And it was 3 parties, yes.
And are these MPC protocols, I forget Maestro, but they're usually offline, online. The timings that you gave, are they end-to-end timings or just the online phase?
So this is for creating the one-hot vector, so with all the communication and stuff like that, yes.
So it includes like... Okay. Thanks.
Is there any assumption about the number of parties as well?
You mean?
Yeah, like some of the MPC protocols, they assume two-party at most, or
But you mean
you mentioned three parties?
in what protocol or what?
All parts that you presented.
I mean-
are there any constraints on the number of parties in any underlying?
I mean, our CoSNARK's repo, at least for the witness generation, relies on rep-free, so free parties. For the proving, we also have a Shamir implementation where you can have more parties. Yeah.
Thanks. I have a question on the lookup when you're doing the count values for the hash. You mentioned that there would be one round for each and every index, or for all index on that? When you're doing the counting the indices, I think specifically for some.
So the counting for the looked up values, you mean?
Right. Yes.
Yeah, I mean it's one communication round for each of these
each
one-hot vectors. Yeah.
Okay. Thank you.
Yeah, there is still some improvements to be made. Yeah, sure.
I wanted to ask about the tooling and how much, like, when you're writing a new circuit, do you have to always start from scratch, or there are like, does the CoNoir allow you to do things without having to do all the basic things again? Do you know what I mean? Like, if I was to write new circuits,
Yeah.
do I have to go back to scratch and figure out the lookup stuff, or are there good enough tooling that I can just do it at a high level and it would?
You mean like save it for later?
Like, you know how what Noir did for circuits basically is give a high level. It had already some standard library, you know, things like JSON parsers and stuff. You don't have to do that again every time you're writing a circuit.
I mean, you can just do, let's not say all, but most of the Noir circuits just run with our tooling. Yeah.
Okay, cool.
I have a similar question regarding circom circuits. Will most of the, like if the existing circom circuits can just use the CoSNARK GitHub and compile and work with CoSNARKs, or is there a lot of are there some edge cases that you have to be wary of?
No, you can, I mean, there are maybe some cases which don't work, but basically you can just use the circum circuit and run it with our tooling, yes.
Oh, okay.
Lovely. That's the talk concluded. So thank you very much, Florin. And it's break time. Lovely. Thank you.
Thank you.